is trying to understand the ingredients for life that were present on the early Earth and might be elsewhere in the solar system. And then somebody else's research to say, okay, given those ingredients, here's how life got started. And I think that's a harder question. At least I'm able to make actual measurements of real samples and figure out what was there. And then you're into speculation to try and figure out how that turned into life. But what we try and do is look for organic compounds that are necessary to life, things like amino acids, nucleobases, other small molecules that are essential for life, and figure out where they came from and how they might have been delivered to or formed on the early Earth. And so we do that in a bunch of different ways. Actually, here's a nice little cartoon that shows all this different areas of prebiotic chemistry. So you have a lot of chemistry going on out in the interstellar medium, in the dense molecular clouds where stars and planetary systems form. There's chemistry going on there, and then when a planetary system forms, it inherits a lot of the compounds from those clouds. And so what I do is look at this region of the cartoon when we're looking at things like meteorites or interplanetary dust particles, remnants of comets or asteroids, small bodies in the solar system that are in some ways a snapshot of the chemistry of the early solar system. The pristine material, we're trying to figure out what was there. There's also this part of chemistry that can happen on a planetary surface, things like hydrothermal vents or volcanoes or Miller-Urey atmospheric conditions, reactions, things like that. And so what we don't know is the relative importance of all these things, the organics that were delivered from space, the organics that were formed on a planetary surface. But we're just trying to understand what that full inventory was and then see if there are any clues there that help us understand why life uses certain molecules and not others, what the choices are that have been made. And so we do that in our lab in a lot of ways. Sort of the bulk of our research, a lot of our research is studying meteorites. So if you've never held a meteorite, there you go. That is a piece of the Allende meteorite. It's a carbonaceous chondrite type of meteorite. So these are meteorites that contain a few weight percent carbon. And that's the oldest thing you'll ever hold. That's older than dirt. It's older than any rock on Earth because the whole Earth weight has undergone melting and reprocessing since formation. But that formed in the solar system formed 4.5 billion years ago. And the little white inclusions are the oldest solid material in the solar system. Hello, sorry. That's okay. I was passing around a meteorite. So I guess the oldest thing you'll ever hold. And the little white inclusions there are the oldest solid material in the solar system. So they're calcium aluminum inclusions. And what we try and do is look at these, which is 4.5 billion years old. Do you want to hold it? Or?
Okay.
Yay. 4.5 billion year old material that's really a snapshot. It formed when the solar system formed. And trying to understand what the organic compounds are that are in it and how that relates to the ingredients that were necessary for the origin of life on Earth and the potential for life elsewhere. And so we take these really old, pristine materials, these meteorites, we grind them up into a powder, and we basically make meteorite tea out of them. So we seal them up in an ampule with some solvent, usually just water, sometimes a weak acid, depending on what molecules we're interested in. And we heat it up to boiling for 24 hours, and we pull out basically the soluble organic material. And once we have that out, we do a little bit of chemical cleanup on it, and then we can take it next door to analyze it and figure out what's in there. And so, like I said, we do a lot of our work looking at amino acids. In meteorites, amino acids are the building blocks of your proteins. They're essential for life. We're finding them in all sorts of different meteorites. We're trying to look at the distribution of amino acids to understand the chemical formation processes that occur in these different environments and clues about how they're related to the amino acids used by life on Earth. We also look at things like nucleobases and we're looking at other small compounds as well now. So we do a lot of work with meteorites. We do a lot of work with returned samples as well. So I don't know if you know the Stardust mission.
Yeah.
So that launched in '99. It flew through the coma of a comet, and it had this one actually. It had this tennis racket-shaped collector full of aerogel, which is a spongy glass material, and it basically flew through the coma of the comet, and the particles from the coma got embedded in the aerogel, and then it got returned to Earth. And we were able to analyze some of that material. We didn't analyze the individual cometary particles because they're too small for our techniques. But we measured some of the comet-exposed material and detected the first amino acid in the comet that way. We're ramping up now and are excited about the OSIRIS-REx mission. Have you guys been hearing about that?
Yeah.
Did you get a sticker yet?
No. Yes.
Stickers. Here.
Oh my gosh. Oh, stickers. Oh, wait.
So
Here,
Star
I
Trek,
have a sticker.
you know, you've heard because it's a God Advantage mission. It's going to launch next September 2016. It will go to asteroid Bennu. Here's our shape model of asteroid Bennu. The real asteroid is half a kilometer across, but that's our best shape model info on it now. And it's going to get to the asteroid in 2019, 2020, I forget exactly. And it's going to spend a year just studying the asteroid, getting optical measurements on it and various remote sensing measurements on it. And then the team will choose some sampling sites, and it goes down and it touches and collects somewhere between 60 grams and 2 kilograms of regolith, pristine regolith from this asteroid. And it'll be back in 2023. And so we're really excited about that because all of these meteorites that we study, they're great. We know they're pristine, we know they're old. We don't have any idea what parent body they came from in space. So there's only a few meteorites that we can tie to a specific asteroid or planet or specific parent body. And so this is going to give us the chance to know something about the parent body and have the sample in the lab to study it.
When did you say that's launching again?
September 2016,
oh,
and it'll return in 2023. Yeah, it's coming up soon.
Yeah.
We've been giving these stories and saying this for a long time, but it's actually coming up very soon.
Great.
And one of the things that our lab is doing now as they're building the spacecraft is helping with contamination studies. So we really want to make sure that the spacecraft and the sampler are as clean as possible before it launches, so that when the sample comes back, that's as clean as possible. When we're looking for things like amino acids that are present everywhere on Earth, we're always having to worry about contamination and rule out as much contamination as possible. So now, as the spacecraft is being built, there are witness coupons, which are basically pieces of aluminum foil that are traveling around with the pieces of the spacecraft through the same environments. And periodically we get samples sent here to analyze, so we can say, yes, you're still below the carbon contamination limit, or hopefully we won't have to say this to them, oh, you have too much contamination, you need to clean again. And one of the other things we worry about with these return samples, there's a contamination limit, we're trying to get it really clean, but you can't account for everything. Like, after 7 years in space, who knows about some of the lubricants, some of the other materials on the spacecraft that might volatilize or creep or somehow affect the sample. So there's archiving going on of all the material that's being used for the spacecraft. Portions are being archived so that when the sample comes back in 2023, we'll be able, if we see a really weird signal, we'll be able to rule out some sources of it. So anyway, we do separate return samples. I also have a paper that I just submitted looking at lunar samples from the Apollo 16 and 17 missions, and looking at amino acids there. So that's a question. Obviously, when the lunar samples came back, there was a lot of interest in organic content of the moon, and there are many studies done, careful studies done, looking for amino acids, but they were always around the detection limit, and they couldn't decide for sure if it was contamination or where they came from. We said, oh, 40 years have gone by, surely we must be able to do better. And so we did a re-examination of these, and put it a little bit better. We could determine that there are amino acids there. A lot of it looked like terrestrial contamination. Some of it looked like meteoritic infall to the lunar surface. So we really like sample return missions because they let you archive this material and revisit it, decades from now when there's better techniques. So we do a lot with meteorites. We do a lot with return samples. We do some work with lab simulations. So there's like the dust lab across the hall that's trying to simulate chemical conditions in the early solar nebula. There's an ice lab here at Goddard that simulates interstellar ice chemistry or chemistry on icy outer worlds, and we could do some analyses for them as well. But basically, it's all trying to determine what organics are present and what that tells us about chemistry and the chemistry taking place in different environments. So we can go next door in a minute, and I'll show you our analytical lab. This is our sample prep lab. It's our cleanish room. It's not really a clean room, but it's where we do all the meteorite preparations and everything. See, but this room's actually a little harder. This is good with a small part group. It won't be too loud next door. If you guys have any questions, you can comment out.
Do you guys get do you get the meteorites from Johnson? I've actually seen the meteorite lab.
Oh, nice. Yeah. So
there's just wondering.
they're much better clean lab than we are. We get most of our meteorites from the Antarctic collection that's curated at Johnson. So you probably know. I don't know you guys. There's a NASA-funded, NSF, Smithsonian-funded team that goes down to Antarctica every Antarctic summer and collects meteorites there. Meteorites fall all over the Earth, but in Antarctica, they're A, somewhat easier to spot because they're sitting on top of ice. B, the ice fields, the ice glaciers move and act sort of like a conveyor belt. So meteorites that fall in a wide range can get concentrated up against the base of the mountains where the team can go. And C, hopefully there's less contamination there because there's not so much life. So there's this team that goes down, they collect usually somewhere between 200 and 1,000 meteorites each year, and they're curated in the curation lab at Johnson. And so yeah, for the Antarctics, we write down a sample request to get those. We also get meteorites like the Yende, well, this one's not research quality anymore, but the non-Antarctic meteorites that have fallen elsewhere and been collected. We just write to various museums like Smithsonian for practicing a lot of meteorites. But yeah, that's cool that you've been there.
Yeah, I was working at Marshall last summer on not a meteorite recovery project exactly, but I was tracking bright meteors and like estimating about where they would fall.
Cool.
So we actually got to go meteorite hunting one day. We didn't find anything.
Well,
because it was like,